The bottom of the ocean is often imagined as a flat, dark floor, a final layer of mud beneath all waves. That image is simple and comforting. It gives the sea a base, a boundary, a place where the descent ends. The real ocean floor is far stranger. It has mountains, trenches, canyons, plains, volcanoes, coral forests, brine lakes, vents, seeps, landslide scars, impact layers, wrecks, bones, microbes, and sediments that preserve the memory of climate. Most people will never see it directly. Even those who cross the ocean many times travel only on the roof of a hidden world. Beneath the hull lies a vertical distance measured in kilometers, then a landscape shaped by forces older than human language. Some places are smooth with fine sediment. Some rise into seamounts that create islands of life. Some split open along ridges where new crust forms. Some plunge into trenches where pressure becomes almost beyond imagination. To ask what is really at the bottom of the ocean is to ask what Earth looks like without air, sunlight, weather, roads, forests, or cities. The answer is not emptiness. It is another geography, mostly unseen, slow to change in some places and violently active in others. The seafloor is the largest physical landscape on the planet, and much of it is still being revealed. The first truth about the ocean floor is that our map remains incomplete. Satellites can infer broad seafloor shapes by detecting gravitational effects on the sea surface, but detailed mapping requires ships equipped with multi-beam sonar. These ships send sound pulses downward and measure their return, building high-resolution bathymetry line by line. The process is powerful, slow, and expensive. As of April 2026, about 28.7% of the global seafloor had been mapped with modern high-resolution methods. This means that much of the ocean bottom is still known in broad outline rather than close detail. We may know that a ridge or basin exists while missing smaller features that matter for geology, habitats, hazards, and navigation. This unfinished map is one reason the bottom of the ocean continues to surprise us. New seamounts, vent fields, coral gardens, landslide scars, and biological communities can still be identified. The seafloor is not a blank space waiting for names. It is a world already full of structure. Human knowledge is the part still catching up. A large part of the ocean floor consists of abyssal plains. These are vast, deep, relatively flat regions covered by fine sediment. They often lie between 4 and 6 kilometers below the surface. At first glance, they can seem empty: cold water, darkness, mud, and scattered animals. Yet their apparent simplicity hides one of the largest habitats on Earth. Sediment falls slowly from above. It contains dust, shells, microscopic remains, organic particles, volcanic ash, and chemical traces from the water column. Over long timescales, these layers build a record of changing climates, ecosystems, and ocean chemistry. A core taken from abyssal sediment can hold information from thousands or millions of years, depending on location and accumulation rate. Life on abyssal plains is often sparse but varied. Sea cucumbers process sediment for food. Brittle stars extend arms into currents. Worms burrow. Crustaceans scavenge. Microbes transform organic matter and influence chemical cycles. Small disturbances can matter because recovery is slow. The abyssal plain looks quiet because time there moves differently from time at the surface. The ocean floor is covered with mountains. Seamounts rise from the seabed but do not reach the surface. Some are extinct volcanoes. Some are part of chains created as tectonic plates moved over hotspots. Others form through complex volcanic and tectonic processes. There may be tens of thousands of significant seamounts across the global ocean, and many remain poorly studied. Seamounts matter because they interrupt currents and create habitats. Water moving around them can generate upwelling, turbulence, and localized productivity. Deep-sea corals, sponges, fish, crustaceans, and other organisms can gather on their slopes. For animals traveling through the deep ocean, seamounts can serve as feeding grounds, navigation points, or biological islands. They are also vulnerable. Fishing gear can damage slow-growing coral and sponge communities. Mining interest may increase in some regions. Because many seamount organisms grow slowly and live in specific conditions, damage can persist for a long time. The underwater mountains of the ocean are not lifeless stone. They are habitats rising through darkness. Running through the ocean basins is the largest mountain system on Earth, the Mid-Ocean Ridge Network. Here, tectonic plates move apart, magma rises, cools, and forms new oceanic crust. The ridge system winds around the planet for tens of thousands of kilometers. It is one of the clearest signs that Earth's surface is active and constantly renewed. Along parts of these ridges, hydrothermal vents release hot, mineral-rich fluids. Seawater seeps into cracks, heats near magma, dissolves minerals, and returns to the ocean through chimneys and fissures. Around some vents, ecosystems flourish without sunlight, supported by microbes that use chemical energy. Tube worms, mussels, shrimp, crabs, snails, and microbial mats can gather in dense communities. The mid-ocean ridges show that the bottom of the ocean is a place of creation. New crust is born there. Heat escapes there. Minerals build chimneys there. Life gathers there under conditions once considered impossible. The seafloor is not only a place where things settle, it is also a place where Earth makes itself. At the opposite extreme from ridges are the trenches. These deep, narrow depressions form where one tectonic plate bends and sinks beneath another. Trenches include the Mariana, Tonga, Kermadec, Japan, and Peru-Chile systems. The deepest known point, Challenger Deep, lies in the Mariana Trench at roughly 10,935 meters below the surface. The Hadal trenches are among the most extreme environments on Earth. Pressure can exceed 1,000 times that at sea level. Temperatures are cold. Sunlight is absent. The terrain can be steep, unstable, and difficult to explore. Yet trenches contain life, amphipods, microbes, sea cucumbers, worms, and specialized fish in certain depth ranges. Organic material can accumulate in trench basins, feeding unexpected communities. Trenches also reveal the planet's violence. They are linked to subduction, earthquakes, volcanic arcs, and tsunami-generating events. The bottom of the ocean is not only deep mud and strange animals. In trenches, it is the visible edge of Earth recycling its crust. Submarine canyons cut into continental margins, sometimes extending from near the coast into deep water. They can be as dramatic as canyons on land, with steep walls, channels, and branching systems. Some are shaped by ancient rivers when sea levels were lower. Others are carved and maintained by underwater flows of sediment known as turbidity currents. These canyons can transport sediment, nutrients, organic material, and debris from shallow waters into the deep sea. They are corridors between the continents and the abyss. Strong currents and sediment flows can move through them with great force, reshaping the seabed and sometimes damaging undersea cables or infrastructure. Biologically, submarine canyons can be rich habitats. They concentrate food, create varied terrain, and support corals, sponges, fish, crustaceans, and many other organisms. A canyon beneath the sea is not a static scar. It is a passageway where geology, biology, and gravity interact. In some parts of the seafloor, dense salty water gathers into brine pools. These pools can look like lakes beneath the ocean, with a visible surface separating the dense brine from the seawater above. They form where salt deposits dissolve or where highly saline fluids seep from the seabed. Because the brine is much denser than surrounding seawater, it settles into depressions. Brine pools can be toxic to many animals because of their chemistry and low oxygen levels. Creatures that enter may die along the edge, creating eerie scenes of preserved bodies and scavengers. Yet specialized microbial life can exist around these environments, using chemical gradients in ways that surface life rarely experiences. These underwater lakes are unsettling because they challenge intuition. At the bottom of the sea, there can be another body of water with its own shoreline, density, and chemistry. The ocean floor is not merely solid ground beneath water. It can contain liquid boundaries hidden inside liquid space. cold seeps occur where fluids rich in methane, hydrogen sulfide, or other chemicals escape from the seafloor at relatively low temperatures. Like hydrothermal vents, they can support life through chemosynthesis. Microbes use chemical energy, and animals such as mussels, clams, tube worms, crabs, and other organisms may gather around them. Some seeps are associated with methane hydrates, ice-like structures that trap methane within water molecules under high pressure and low temperature. These deposits are important for carbon cycling, geohazards, and climate research. Disturbance of methane-rich sediments can affect seafloor stability in some settings, though the processes are complex. Cold seeps show that the bottom of the ocean leaks chemistry. The seafloor is permeable, reactive, and alive with microbial processes. What looks like mud may be part of a hidden exchange between Earth's interior, sediments, water, and life. Coral is often associated with warm tropical reefs, but deep-sea corals grow in cold, dark waters across many parts of the ocean. They do not rely on sunlight in the same way many shallow reef-building corals do. Instead, they capture food particles from the water. Some form complex structures that provide habitat for fish, crustaceans, worms, sponges, and other organisms. Deep-sea coral gardens can occur on slopes, seamounts, ridges, canyons, and continental margins. They may grow slowly and live for long periods. Their structures create shelter and feeding opportunities in environments where hard habitat may be rare. They are among the most beautiful ecosystems on the seafloor, though most people will never see them. These coral forests are vulnerable to physical disturbance, especially from bottom contact fishing gear. Because they grow slowly, damage can last for decades or centuries. The bottom of the ocean contains living architecture that is both hidden and fragile. The ocean floor contains the remains of animals and people. Whale falls become ecosystems, feeding scavengers and microbes for years. Shark teeth, fish bones, shells, and microscopic skeletons settle into sediment. Human wrecks add metal, wood, cargo, fuel, plastic, glass, and memory to the seafloor. Aircraft, submarines, lost containers, fishing gear, and cables all become part of the ocean's material record. Marine debris has reached even extreme depths. Plastic fragments and other human traces have been found in deep-sea environments. The seafloor is therefore a natural archive and a human archive at the same time. It records evolution, climate, geology, trade, war, industry, and waste. This mixture is one of the most powerful truths about the bottom of the ocean. It is ancient and modern at once. A sediment layer may preserve climate signals from long before civilization, while a nearby plastic object may have arrived within a human lifetime. The abyss holds deep time and consumer time together. Much of what is really at the bottom of the ocean is too small to see. Microbes live in sediments, on rocks, around vents, within crustal fluids, and in chemical gradients near seeps and brine pools. They break down organic matter, cycle nutrients, transform minerals, consume methane, and support ecosystems based on chemical energy. Some microbes live beneath the seafloor, in sediments and crustal environments where energy is limited and metabolism may be extremely slow. These communities challenge assumptions about the limits of life. They show that the biosphere extends below the visible seafloor into hidden habitats of rock, pore water, and chemical reactions. The microbial bottom of the ocean may be one of the most important parts of the planet's life system. It is quiet, invisible, and vast. It links biology with geology in ways that science is still learning to measure. The bottom of the ocean is often treated as the final place, the end of descent. In reality, it is a beginning for many processes. New crust forms at ridges. Old crust sinks at trenches. Sediments archive climate. Microbes transform chemistry. Vents feed life. Canyons carry material downward. Corals build habitat. Whale falls create temporary cities. Wrecks become reefs or hazards. Debris becomes evidence. This is why the ocean floor cannot be reduced to mud. Mud is there, in enormous quantities, but so are mountains, faults, volcanoes, minerals, fluids, animals, microbes, and histories. The bottom of the ocean is the planet's hidden foundation, active in ways that rarely reach the surface of human attention. When waves move above, the seafloor remains out of sight, yet everything is connected. Currents interact with terrain. Nutrients rise from deep waters. Carbon sinks into sediment. Earthquakes displace water. Vents release heat. The surface ocean is shaped by a bottom most people never imagine. Sediment may seem like the least dramatic substance on the seafloor. It settles quietly, grain by grain, through dark water. It buries wreckage, softens ridges, fills depressions, and muffles the shape of older events. Yet sediment is one of the great authors of the ocean floor. It records climate, volcanic eruptions, microscopic life, dust from distant continents, chemical shifts in the water column, and the remains of organisms that once drifted in sunlit seas far above. In some places, sediment accumulates so slowly that a few centimeters may represent centuries. In others, rivers, storms, glacial grinding, and margin collapse can deliver much larger quantities. The result is not a uniform blanket, but a layered archive whose meaning changes from basin to basin. Fine red clays may settle in one region. Calcareous oozes made from tiny shells may dominate in another. Siliceous deposits may mark waters rich in certain plankton. Black, organic-rich layers can speak of ancient low-oxygen events. Scientists recover these stories through cores driven into the seafloor. When those cylinders of mud and sediment rise to the deck, they carry a vertical history of the ocean. Each change in color, texture, grain, shell content, chemistry, or fossil composition can reveal a change in the world above. A colder climate, a warmer interval, an ice sheet pulse, a volcanic episode, a shift in circulation, all may leave subtle traces in the floor of the ocean. Sediment also shapes habitats. Some animals need soft mud for burrowing. Some prefer firmer ground. Some feed by sorting through particles for organic material. Microbes occupy the spaces between grains, where chemistry changes with depth below the sediment-water boundary. Oxygen may disappear quickly in some places, giving way to other metabolic pathways. Even apparently featureless mud plains can contain invisible structure, with gradients of chemistry and life extending downward into the seabed. The quietness of sediment is therefore misleading. It is not passive dust. It is a patient form of planetary memory. It hides, preserves, transforms, and records. The bottom of the ocean is partly written in stone, but much of its meaning is stored in mud. The bottom of the ocean is often described as ancient, silent, and still. In one sense, this is true. Large regions change slowly, measured in geological time. But the seafloor can also move with startling violence. Earthquakes rupture faults. Landslides collapse continental slopes. Turbidity currents race through submarine canyons. Volcanic eruptions fracture ridges and build new lava fields. In a matter of minutes, a quiet, deep landscape can be torn open, buried, displaced, or set in motion. Submarine landslides are among the least visible but most consequential of these events. Vast masses of sediment and rock can fail on continental margins, especially where steep slopes, gas-rich layers, rapid deposition, or earthquake shaking weaken the ground. When such failures occur, they can damage cables, reshape habitats, and in some cases contribute to tsunamis. The ocean floor keeps the scars of these collapses, but from the surface there may be little immediate sign beyond a passing wave or a break in communications. Turbidity currents are another hidden force. These dense underwater flows, loaded with sediment, can rush downslope through canyons and channels like rivers of moving earth. They are capable of traveling great distances and cutting into the seabed with enormous energy. In the deep past, such currents built submarine fans of remarkable scale. In the present, they can still threaten infrastructure placed on or near the seafloor. This movement matters because it reminds us that the bottom of the ocean is not only a destination for falling material. It is also a dynamic landscape shaped by sudden release. The same seafloor that records history can rewrite itself. A cable route that seems secure can be severed. A habitat can be buried. A channel can be cleared and deepened by force. In darkness, motion continues. One of the least appreciated realities of the ocean floor is that modern civilization rests on it more than most people realize. Submarine cables carry the vast majority of intercontinental digital traffic. Messages, financial transactions, streaming media, business systems, scientific data, and personal communication all move through lines laid across the seabed. To think of the ocean floor only as wilderness is to miss that it is also part of the hidden infrastructure of the contemporary world. These cables cross abyssal plains, continental slopes, and sometimes more hazardous terrain. Engineers choose routes carefully, avoiding where possible the most unstable zones, fishing pressure, and sharp topography. Even so, cables can be broken by anchors, trawling, earthquakes, turbidity currents, and slope failures. A break on the seafloor can ripple outward into economic disruption, slower communication, and strategic concern far above the waves. The presence of cables changes the emotional meaning of the deep ocean. It is not just remote, it is operational. The seafloor hosts the quiet threads of globalization, lying in darkness beneath shipping lanes and storms. Vast distances of ocean that look empty from space contain narrow lines of extraordinary importance. A person sending a message from one continent to another may imagine satellites and air. Often the signal travels through glass fibers resting on the bottom of the sea. This hidden network also creates political and strategic significance. A cable route is infrastructure, and infrastructure can be vulnerable. The deep sea floor becomes a space of attention not only for science but for states, industry, and security planning. What lies at the bottom of the ocean is therefore not only natural terrain, it is also a foundation for the human systems that connect the world. The future of the ocean floor is now part of public debate because human activity is moving downward. Deep-sea mining proposals focus on polymetallic nodules, seafloor massive sulfides, and cobalt-rich crusts, all of which occur in different geological settings on the seabed. Supporters speak of metals needed for modern industry and energy systems. Critics point to ecological uncertainty, slow recovery, and the risk of damaging habitats before they are properly understood. This debate reveals how incomplete our knowledge remains. Nodules on abyssal plains may appear inert at first glance, yet they can provide hard substrate for organisms in otherwise soft sediment regions. Vent systems targeted for their mineral deposits may host endemic life uniquely adapted to those chemical environments. Sediment plumes created by industrial disturbance could spread beyond the immediate site, affecting filter feeders and benthic processes in ways that are still being studied. There is also a deeper philosophical issue. The seafloor has long been protected by difficulty. It was not untouched, but in many regions it remained beyond ordinary industry because access was too hard and too expensive. That barrier is weakening. As technology improves, the bottom of the ocean shifts from remote frontier to contested zone. Extraction, conservation, research, cables, military interest, fisheries, and climate science all meet there. The question is not only what is at the bottom of the ocean now, it is what kind of place humans will allow it to remain. A hidden landscape can be treated as sacrifice space because few people will ever see it. Yet invisibility is not emptiness, and remoteness is not consent. The bottom of the ocean is living, historical, and connected to the rest of Earth. Decisions made about it will not stay there. What is really at the bottom of the ocean is a second Earth beneath the familiar one. It has plains wider than countries, mountains higher than many on land, trenches deeper than Everest is tall, forests without sunlight, lakes beneath water, chemical cities, graveyards, archives, and living mud. It is dark, cold, pressurized, and still incomplete in human knowledge. The seafloor matters because it supports life, records climate, shapes hazards, stores carbon, holds resources, and reveals how the planet works. Its mystery is not emptiness. Its mystery is complexity hidden by depth. We have crossed the ocean for centuries while barely seeing the world below the hull. The bottom of the ocean is not the end of the planet. It is one of the places where the planet is most itself, slow, violent, alive, ancient, and unfinished. Far below the waves, Earth keeps building, burying, feeding, breaking, and remembering.